Nice slide.
All right, thank you, everybody. Thanks for coming to our CAN seminar series presentation for today. This week, we are indeed fortunate to have with us one of our visitors, one of our speakers from out of the country even, but not so far away, just South America, from Colombia. We have Dr. Silvia Caro from Universidad de los Andes.
Very good.
Actually, yes, that's where she graduated from, and her BS undergrad and master's degrees are from Los Andes University, and now she's a professor there. She has been a professor since 2009 when she got her PhD from Texas A&M University, and she's been focusing on asphalt materials. So one other thing about Silvia is she's also taken over to become the first vice president of the new Academy of Pavement Scientists and Engineers. So she's very involved in pavement engineering and science, and of course working with us and the pavement community on that, so for hopefully many years to come. We're indeed fortunate to have her talk to us on some recent research she's been doing, and hopefully she will continue to do a lot of these great research efforts, although she's a new vice dean, and congratulations for that, in the School of Engineering. Such a young age again, great, anyway. But
he said before he didn't know you congratulate me or give me the condolences. So
I didn't want to mention that. So, we know she'll continue to do really good work in pavement engineering. All right. I shouldn't talk a lot more, but she'll let me actually, let's give her a big round of applause here. Welcome
Thank you.
to join with us and give us the seminar.
Well, thank you very much. I'm very, very happy to be here. It's an honor, and I appreciate the invitation from Dr. Al-Kadi, Dr. Ozer. It's really a pleasure to be here. It's my first time in Illinois, and up to now, everything that I have seen, I have loved it. So very excited, and thank you very much for being here. So I'm going to talk today about recent work we have been conducted in our research group about the mechanical properties and the influence on those properties in asphalt mixtures when you have unsaturated conditions. But before that, and very briefly, I wanted to let you know where I'm coming from. So this is Colombia, and we have two more people from Colombia here, Jaime and Daniel, which is located in the northwestern corner of South America. Very convenient position. We are the only country in South America with access to both oceans. The size of Colombia is around 1 million square kilometers. For you to have a good reference, it's around 6.5 times the size of Illinois. We have 44 million inhabitants, and we have borders here with Ecuador, Peru, Brazil, Venezuela, and Panama. And the capital city is Bogota. And if you look at how is the topography in our country, well, we have the Andes, which are the big mountains that come from Chile, Peru, Ecuador, and when they arrive to Colombia, they open in 3 branches. And if you see where the people live, this is a map of population, well, you conclude that people live in the mountains, basically, and a little bit in the north coast. So 80% of the people live here. And if you start seeing the natural hazards maps, like seismic hazard, you will see that people live exactly where the highest hazards are located as a consequence of the topography. So that makes a big challenge for us in terms of, for example, connecting the country. Every time that we need to build roads, we need to go from one mountain chain to the other. So that's very important, and it's one of our main challenges right now in the country. And right here in the eastern branch of the Andes, on top of the mountain, you find the city. This is Bogota. It's very high in altitude, 2,600 meters over the sea level. For those of you that use the US or English units, is 8,500 meters over the sea level. Temperature is perfect. I like it. It's between 7 degrees and 22 degrees, or 44 Fahrenheit and 71, all year long. We don't have seasons. We are in the tropics. So that's the temperature always. And we are about 8 million inhabitants. And right there, like you can see here, there is a famous church that is called Montserrat. If you go down to that church, you find our university. And this is the School of Engineering. So I'm coming from Universidad de los Andes. And we always clarify that it's from Bogota, Colombia, because there are two other Universidad de los Andes, one in Venezuela and one in Chile, and we are not related. So those three are different universities, but we share the same name. Why? Because all of them are located in Los Andes, so in the Andean region. So our university is a private one. It's a very young university. It was founded in 1948, which means that next year we are celebrating our 70th anniversary. We have around 19,000 students. We are the first university in Colombia. And depending on the ranking, we are between the 5th and the 8th university in Latin America, which is very important for us because we are competing with these big public universities like Sao Paulo, Mexico National University, etc. All our engineering programs are ABET accredited right now. And I belong to the Department of Civil and Environmental Engineering that has around 2,000 students and around 25 faculty members. So this is very quick just for you to show you some pictures of the university and to invite you, if you by any chance go through Bogota, you are more than welcome to come and visit us. So you just need to contact me and I will make everything for you to have a nice visit. So we have a very nice campus. It's not that big, but it's nice. And as I mentioned before, this is the engineering school. So that building is the house of all our programs and labs. And we have very nice labs. This is the Civil and Environmental Engineering Integrated Lab with nice equipment. And some of that equipment that you use, for example, in pavements has been homemade. So we are very good we are not. My colleague, I'm going to talk about him later, he's really good at making all this equipment, which is very efficient because allow us to do advanced research at a lower cost, very customized to our needs. So this is, for example, our accelerated loading facility. We have a full-scale centrifuge that was also made in the university. It's small compared to the big-size centrifuge, but it's still considered a full-scale centrifuge. There are only two in Latin America, one in Brazil and this one. So very nice to do geotech physical modeling. That's why we use it for it. And I belong to this group. My research group is called Geomaterials and Infrastructure Systems. This is GeoC. In Spanish, it's GeoC. And I don't know if you know, C means yes in Spanish. So it's a very positive name. It's like Geo yes, basically. So we are, right now, we are 6 members. This is Dr. Sanchez. He's an expert in infrastructure systems, modeling stochastic degradation of infrastructure systems. Dr. Bernardo Caicedo, he's my colleague who is in charge of doing all this amazing equipment. He's half in pavements, half in geotech. We have 2 other professors in geotech, Nicolas Estrada and Dr. Miguel Angel Cabrera. He just joined the department. And we also come with the support of Jaime Wills. He came here last year. He is an instructor. He supports us with some research, and he also helps us with some undergraduate classes. So this is basically our group. And I always make a recognition to our students. We depend on you to do a good level of research. So this is a picture of the students that are working right now in pavements, exclusively in pavements in our group. And you see there is a little bias in terms of male-female. I noticed that the other day. We are missing some students, but we do have a strong participation of women in the group. And this is only a recognition to them because they are fantastic, committed, and very motivated students. And without them, I'm sorry? Yeah, I don't do, it's not too much effort. I don't know how that works, but it works pretty well. So coming back to the technical part. So I'm going to talk to you about the topic I'm going to talk to you today is a collaboration with Dr. Bernardo Caicedo. And we have a PhD candidate student, Eduardo Rueda, and this is basically his work. We also count with the support of Juliette Monroy. She is responsible to help us with all the instrumentation and control systems in all our experiments. And we initiated part of this work with MSc student, Sonia Hernandez. So what I'm going to show you today is a collaboration work between all of us. So I'm sure you have heard about moisture damage and the importance of that topic in the area of pavement engineering. So in the last, I would say, 3 decades, we have achieved very important advancements in better understanding, preventing, and controlling this phenomena. However, even though we have improved a lot, I would say that we still need more information, especially in the fundamentals, understanding what is happening, what is the mechanism that drives the process of moisture affecting the quality of the aggregate binder systems and the cohesive properties of the binders. So that includes, for example, to start studying the individual modes of moisture transport. There are many. To understand the uncertainty of these processes. This is very difficult. The reason why I think one single test for the characterization of moisture damage could not be necessarily the best option for all countries is because you cannot have a universal test that includes climatic conditions from every single part of the world. So that's an important challenge. And the other one is that we are also very strong in our group and like other groups like here in mechanical modeling and computational modeling. But if we want to start studying these mechanical environmental coupled phenomena, we need reliable data, and we don't. So that's another motivation to start including or studying with more detail these processes. So I'm going to focus on one of the modes of moisture transport, which is vapor diffusion, moisture diffusion. You also have infiltration of liquid water. You also have capillary rise. But I'm going to focus on moisture diffusion, which is one of the main modes of transport by which moisture can reach the internal microstructure of these mixtures. If you see, and there are several works published demonstrating this, asphalt pavements are constantly exposed to the diffusion of moisture because of the existence of a gradient between the atmosphere and the lower layers of the pavement. So you are expecting to have moisture diffusing during the life service of your pavement. That means that most of the materials, and we have experts like Dr. Tutumler in unbound granular materials and soils, that they know that it's common to have a partial saturation condition in these materials. So you need another way to understand that, and we have been very good at that in the unbound granular materials, but not in our asphalt mixtures. So why moisture diffusion, and what are the questions that we would like to answer? Well, as I mentioned before, it is always present in pavement structures. However, we don't know what is the impact of having different relative humidity or degrees of saturation in the mechanical properties and the performance of these mixtures. We are very good at the temperature characterization. We know what temperature does to our viscoelastic materials, but not what moisture, in terms of a steady state with a degree of saturation, what is the impact on our materials. So what is the impact on those materials? And a good question is, could it be considered a state variable similar to temperature? Could we do something similar? If I know how much is the temperature and the relative humidity or the degree of saturation, is it possible to have the answer about my material properties? Can I treat this new climatic variable in a similar way? And as I mentioned before, many of us have conducted a lot of computational mechanics models. This one is showing how moisture is entering into a mixture. This is Daniel's models. And we have always assumed what is the impact of that moisture that is entering into the material, to the material properties of that model. Those have always been an assumption, including myself. I did it based on good guesses. I mean, based on material that is reported for polymers and other viscoelastic materials, based on some tests that have tested the material in dry and completely saturated conditions. So we have the extremes and we have assumed the rest, but we really don't know. Luckily for us, other people in other groups and in other areas have used extensively partial saturation theory to try to explain those conditions. So probably we could start using that as well in asphalt mixtures. So the experimental work that I'm going to show you is working on one mixture. And it's a regular super paved dense graded mixture with a nominal maximum aggregate size of 9.5 millimeters. we use an asphalt that is classified as penetration 60-70. It's a PG 58 minus 22 or less. The optimum binder content that resulted from the mixed design was 5.4% by total weight. And we prepare our specimens with a target air voids of 7%. So that's the material we are characterizing. If we change the volumetric properties of this mixture or other characteristics, of course, the results are going to change a little bit. And what is interesting about this study is that we are using a new equipment that we recently developed at the university that is called the hollow cylinder tester for asphalt mixtures, so HCTAM. So it's this apparatus here that permits to apply to an asphalt mixture any type of loading combinations. So we have a vertical actuator and a torsional actuator, a moving piston, the control driver, and our load cells. And our specimen is located right here inside the conditioning chamber. And we can apply axial loading, torsional loading, monotonic, constant, dynamic, simultaneously, or independently. So that gives you a whole range that usually most equipments cannot do it. That will allow us, for example, to have a very complex stress pads applied to the specimen. If we want to study, for example, what happens with the material when you have a wheel load that is passing over, the principal stresses start moving. And most of the tests cannot reproduce those complex stress pads. So you can do it with this equipment. So this is an actual picture of the equipment. It took us almost 6 years to develop the equipment. And this is part of the PhD work of one of my students. He started this as part of his master thesis. So basically, this is it. You can see here the climatic chamber. The specimen is inside, and we have all the system working inside. We recently published in the ASC Committee of Payments Spotlight Research. The chair is Dr. Oster here. And we have a nice video, like a 3-minute video about the equipment if you want to go to the Facebook page and look at it. One important comment is the name, the hollow cylinder tester, is because the specimens are hollow cylinders. And I'm going to show you a little bit more about it. However, I should say this is not the first equipment that has been built to characterize materials. Most of the previous studies are in sands, even goods, and plastics and metals a little bit. But we also have a couple of previous experiences in asphalt mixtures. The first one is from Berkeley, California, Berkeley, with Professor Mona Smith in 1987 and 94. So they made something similar, a little more complex, and with the systems not that advanced. Well, at the moment, that was the technology available. And they started working on that. In fact, John Harvey, when he was a grad student, he was involved helping with some of the experiments. And more recently, in 2013, in Nottingham, Dr. Brown, also with their team in NTEC, they developed a similar machine, a little different, but with the same objective, being able to apply axial torsional loads simultaneously or to create any stress pads that you want. It's big. It's a big equipment. The specimens are very big. And they are using that to study permanent deformation. So they started, they haven't used it in the recent years. So basically, they apply an axial load, and they start applying shear, and they see how is the response of the material, and they characterize permanent deformation with that equipment. So these are the previous two equipments. I would say ours is a little bit more advanced. It has more facilities, and it allows us to do more things. So the specimen, we compact the specimen using the SuperPave giratory compactor, and we do a double coring process. So we take the inner part or inner cylinder out, and also the external shell. So we get finally this specimen that is 12.7 centimeters high, and it has a wall thickness of about 1 inch, basically. So what is perfect about this specimen is that when you apply shear loading, the problem with full specimens is that when you apply shear loading, the distribution of stresses is not uniform. So it's 0 in the center and maximum in the border. But when you have a hollow cylinder, you are only applying stresses in this annular part of the specimen. So it's a little bit more uniform, not fully uniform, but a little bit more, which kind of validates the use of shear loading to characterize the materials. But the second that is fantastic is that we have a double exposed wall, the external and the internal. So for conditioning, in terms of climatic conditioning, it's perfect because it's very fast. If you only have a full specimen, you can expect the material to get conditioned from outside. But when you have a double exposed wall and it's not that much material, we can accelerate all those processes, or those processes take less time. So basically, that's our material. And what we did in this first application with our equipment was to use a technique that is called the vapor saturation technique to condition our specimens at different levels of relative humidity. So exactly what you do in the oven. You take your mixture and you put it in the oven. And if the oven is at 40 degrees, eventually your material is going to be at 40 degrees in a steady state. So we wanted to do the same, but using relative humidities. So basically, the theory says that if you select some salts and prepare some saline solutions in a closed environment, you can produce a controlled relative humidity environment or atmosphere. So we use these salts that are here to produce from 8%, 31%, 46%, 80%, and almost completed saturated condition environment. We put our specimens inside some containers, big containers. So the containers, our specimens are in here, and here, like this is like X-ray from the containers. So here you have the saturated saline solution, and we have sensors, so we are checking all the time that the relative humidity within that atmosphere is controlled. So if the specimen, let's say typically in our lab, the relative humidity is around 60%. So if the saline solution is less than that, then the material is going to start losing weight because it has to adapt to a less humid environment. So we are controlling using gravimetric techniques, which means that we control the weight of the specimen day by day. And we see if the specimen is losing weight or gaining weight if we put it in a more humid environment. And when the material doesn't change the weight, it means that it reached a steady state condition. At that point, we know that all the specimen has exactly the same relative humidity that the environment, which is very nice. We have never done that for asphalt mixtures. We usually take the mixture, submerge the mixture, and we take it out, and we know that it's almost near saturation, but not necessarily it's in a steady state condition. So that's what is very nice about it. So once the mixtures are in that condition, we take the mixtures out and we put it inside our chamber. And inside our chamber, we have a very special environmental system that has exactly the same relative humidity environment inside the chamber. So there are no changes within the specimen. We made that using a relative humidity recirculation unit. So within that chamber, we can control temperature. We have a thermostatic bath. So temperature here is controlled, and also the relative humidity. We also have, if we want to use it, a high air pressure system in case we want to couple several climatic conditions that could be useful for aging, for example. But for this experiment, we kept temperature at between 20 and 25 degrees constant, and the relative humidity that we already achieved. If we start changing the temperature, the mixture, the internal humidity of the mixture is going to change. So we are keeping temperature constant for those reasons. And once we had that, well, we can start doing mechanical testing. So what we did initially was to do a dynamic modulus test, axial, and then also torsional. And we wanted to see for different frequencies, we did a frequency sweep test, how the relative humidity within the specimens was affecting the material properties. And here is very important, the feeling or the intuition. Most of us, including myself, were thinking that the higher the relative humidity, the lower the modulus. It's like very intuitive for us because we know that moisture is like doing something, degrading the material. But the initial results were different. And I have to say that before this study, we also conducted some basic initial study with mortars, asphalt mortars. And I know that you also have that specimens are little, like finger specimens of mortars that you can implement or use the rheometer to characterize the materials. So before this study, we also did a previous study with mortars, and we already had some clues about what was going on. But we wanted to see what was the response with asphalt mixtures. And basically, initially, what we can get that is very nice is that we can get two important graphs: the relationship between relative humidity and the degree of saturation of the mixture. And the second one that is very used, commonly used by people in unbound granular materials, which is the water retention curve, a fundamental property of the material that tells you what is the relationship between the degree of saturation with suction within the material. And surprisingly, we only found one more paper reporting retention curves in asphalt mixtures. And it's quite simple. From the gravimetric analysis that we were doing, we can compute that. So if we combine this and this one, we can have, for example, at 40% of relative humidity, what is the equivalent in suction. And better, we can express our results in terms of the degree of saturation of the specimen, not the relative humidity of the environment, but how much water is inside our specimen. So those were two initial results from the conditioning process that we get. And this is the result of the impact of the degree of saturation for different frequencies on the dynamic modulus of the material. So kind of surprising, you start seeing that the higher the degree of saturation within the material or the relative humidity, the modulus starts decreasing until reaching a minimum. And after that, it starts increasing. But it's also affected by frequency. If you have 20 hertz, the impact is going to be higher than when you have a very low frequency of almost 0.1 hertz. So very interesting result. Most of us in our models have assumed that it used to go down, permanently down. What it shows here is that it goes up. And the reason for that is kind of logic. And it's those minimums that we have here. If you see the difference with respect to the minimums are very important. With respect to the minimum, the maximum value of modulus when it's near saturation is almost 100% higher. And when it's very dry, it's 23% higher. But when you have a lower frequency, those differences are much lower. But very, very interesting. So it depends on frequency and the degree of saturation. We have never taken that into account in any of our designs or models. So what and the phase angle, we also measure the phase angle from our specimens, so it's basically the same but the opposite. Yeah, so higher the phase angle up till you reach a point when the modulus starts decreasing, the phase angle starts decreasing. So what we believe that is happening, and this is one of the results, is when you have very low degrees of saturation, which means very high suction levels, well, what we believe is that the capillary forces are impacting, and people from experts in partial saturation condition theory knows that. They always say, like, and we know it, when you have low values of suction, then your capillary forces provide the strength to your material. But then water starts getting in, and you start losing those capillary forces. So the modulus starts decreasing until reaching a minimum, after which what we believe that is happening here is just that you have too much water, and water is incompressible. So when you are doing the test, especially during compression, you have the idea that the material is more resistant, and it is. But it's also very problematic because that resistance is associated with pore pressure, which could affect the response of our material. So if you look at published papers on unbound granular materials, you will find something very similar. They have always also found that, which is very interesting, that higher values or near full saturation materials, they show more resistance, but it's in reality due to the presence of water inside. We did something interesting that was trying to see if we could do something equivalent to temperature frequency, but with relative humidity frequency, black space diagram, and cold plot. So if you remember, the black space is a plot of the modulus and the phase angle, and the cold is the storage modulus versus, and it's missing one here, and the viscous modulus. When the material is completely, and we know rheological simple material, and you have temperature, frequency, you see that all the different curves fall into one single diagram, which is perfect. That means that the material is rheologically simple and that we can apply frequency superposition, time temperature superposition principle. But here, look at the results. Clearly, that's of course not the case. We knew that when we saw the plots. And for the cold more or less, but it's different. So if we compare it, this is the classical time temperature response of our black space diagram. See, we did tests at 0, 5, 10, 35, 45, 60 degrees, one single relative humidity, and they all fall in a very nice, smooth curve. The material is rheologically simple. We can apply the time temperature superposition principle. Let's see where our other responses for relative humidity frequency are here, and they are right here. So they shift a little bit, and there are a lot of branches. And something similar with the cold plot. You have all the temperatures there, and ours, that was around 25 degrees, is a little lower. So it's definitely affecting the material properties, only because you have different degrees of saturation. So usually what we use for design are these results. But what we are seeing is that if your mixture is under a different degree of saturation, then the material properties are going to change. That's basically the main message. But we also decide to do something, and it's like we ask about the fact that we have a tension compression test. So can we separate the modulus and see what is the modulus in compression and tension? And it is, yes, we can. We were applying this signal, so we know the signal that is equivalent to tension and compression. So we separated, we uncouple both phenomena. And this is what we get when we only see the modulus in tension, actual tension. So only tension, and I don't apply compression. Tension and relax, tension and relax. And you see here that the influence when you have low degrees of saturation is very high, but not the case here when you have high degrees of saturation. And it's probably because you are doing tension. You are not applying compression to the water. So this is a very nice result. And if we see the other one, which is the compression actual modulus, well, it's exactly the opposite. So the capillary forces doesn't seem to be that much, but look what happens when you have very high degrees of saturation. It's unbelievable. So from all that resistance that we are getting, this is what is driving the increase when you have actual tension compression modulus. We also did, this is a total again. So this part here, we know that is more driven by the tensile modulus, and this one here is when you have compression modulus. We also did shear, and the results for shear are less intuitive. Probably the resistance of water is not that important. Probably the capillary forces are also not that important. So we wanted to know what is the dynamic modulus under shear conditions, and these were the results. So you have, again, the degree of saturation, and you have, in this case, the dynamic shear modulus. And what we wanted to see or to know here is that that trend was also observed or not. And you see that there is a minimum. But when you have very, very low frequency, it's almost independent. The modulus is not affected by the degree of saturation. But when you have higher loading frequency, it's a little bit affected, but it's not that much. So very interesting. So the degree of saturation is affecting the properties, but it also depends on the mode of application of that load. So in conclusion with all this, what you see here is that if we take one of the materials, one of the frequencies, I'm sorry, this is 11 hertz, and you see the degree of saturation, and you see the moduli here, this is the shear, this is the actual tension compression, this is the actual compression, and this is the actual tension. So the effect is very different depending on what you are measuring. So very interesting. That means that probably we need to start thinking about what happens to our mixtures. When you place a new mixture in the field, you're expected to be more on this side because it's fully dry. But then the material is going to start getting saturated because of what we mentioned before about the gradient. So it's probably that you start moving to this side. And probably some models have shown that mixtures tend to get like around 6 months in service after they were built, tend to be near saturation most of the times. But it depends. It depends on weather. So you can be moving. And that's another important point. This is only one cycle, wet, dry cycle. But we do know by previous works that these effects are not totally reversible. So there is certain irreversibility in this modulus. In other words, if you get the material to have a very high degree of saturation and then you dry it and then you wet the material again, probably the property is going to change. It's not going to be the same because the material has memory. It's not the same that with temperature. We know that we raise and we lower and it's reversible, not in this case. So that's basically what we have been doing. These results are quite similar to what we get in our asphalt mortars several years ago. And definitely allow us to start thinking about how we are going to incorporate these findings when we are characterizing asphalt mixtures. So in conclusion, partial saturation does impact the material properties of these mixtures. We already suspected that. I mean, it's a road material. We know that that happens with other types of material. But we notice important differences among axial tension, axial compression, tension compression, and shear moduli. And the differences were even more important at higher frequency levels, always, which is very, very, very interesting, and with higher degrees of saturation. So the higher the degree of saturation, we saw more influence. And this is only the beginning. We are very into this topic, so we need to start working more on this. So these are fundamental material properties. But what about performance? Where is the impact of different degrees of saturation on fatigue life and on permanent deformation? So right now we are studying that. We're starting doing some tests, tension, fatigue, tension, compression test, to see what is the impact of the degree of saturation in the fatigue life of our specimens. And the other important one is that the one that I just mentioned before, is that we do know, because there are previous works published, that the effects of moisture are not fully reversible. So we want to study that irreversibility effects of moisture on both the material properties and the performance. So that means, for example, that we are going to take our specimens and we are going to dry our specimens, then, and take the material properties, compute, characterize the material properties. Then we are going to go to 10% of relative humidity and see what are the material properties, 25, again, until 100. But right after that, we are going to start going back and see it again and dry it again, and then going up again, and then going down again. Because it is very important to know what is the effects of the memory that this material could have, because that's the beginning of degradation. And if we don't know that, we do know the effect of temperature again, but the material is not in the field, is not under a single constant relative humidity. So the idea with all this is to see if we can start better in understanding those complex climatic mechanical phenomena. There is another one which is a little bit more complex. All this is at a single temperature. But in reality, you are also having different temperatures and different relative humidities. So if we condition our specimens, but they are not at 25 degrees as we did, but a higher temperature, well, you have both influences there, temperature and relative humidity. So that coupling is very important if we actually want to understand what is fully happening, because we now have temperature on one side, and with these results, we know what is happening with relative humidity. But with both variables, when that happens, that both variables change, we don't know what is the couple effect. So I think that that's also one of our main challenges. Not sure how we are going to start including this, if it is really important or not. We need to see performance. But apparently, it is important, and we start seeing if this deserves or not to be included somehow in our performance models in the future. So, well, that was basically it. Thank you very much. Muchas gracias. And I don't know if you have questions. Thank you.
first, thank you for the presentation. My question is not about, it's more about how the testing of the mortar is related to the testing of the mixture. You mentioned that the trends are similar, or
yeah, the trends are very similar. In fact, I thought I had those results before, but I didn't want to take most of the time, so we had the space for questions, and I took it away. But they are very similar. Just let me go to, for example, sorry, this one here. So basically, we saw the same with mortars. We had two types of mortars at 10% air voids and 14% air voids. So two different volumetric properties. And what we saw is that they were decreasing. That's shear, right? But the material is a little. All of you know the definition of asphalt mortars. We are talking about asphalt, and usually aggregates pass in sieve number 16, which is 1.2 millimeters and down. So it's like the matrix that you can find in the mixtures. So take away the coarse aggregates, that matrix that lives there, that stays there, is the mortar. So we saw something similar. They were going down up to a minimum, and they start increasing a little bit. But we arrived only to 80%. We didn't go to full saturation. It just took too long. But we saw something similar, not as abrupt as here. Here is even worse, but something similar to the shear results that we show here. Something like this, but we arrive around, this is shifted in mortars. And we arrive around here. I mean, that minimum is around here, and we arrive up to a maximum around 70% of degree of saturation, so more or less. In mortars, we did fatigue as well, and we saw a very strong impact in performance with the relative humidity. Yes?
Thanks for the presentation. So I have like two questions. First one, I think you assume uniform saturation throughout the thickness of AC. Do we expect to see some kind of gradient of the moisture or gradient of the saturation with respect to the thickness of the AC? And the second question, the thickness of your specimen was like around 6 inches, I guess, 5 inches.
The thickness,
yes,
or the height?
Height.
Okay.
Yeah. So did you do any, like how did you come up with this thickness, or did you do any sensitivity analysis with respect to thickness?
Well, yeah, let me recall the first question. Was if?
Like, do you expect to see some gradient of saturation with respect to AC in the field? If you expect to see that, how?
Yeah, definitely.
How did you simulate that in your experiment?
Yeah, in the experiment, it's like exactly with temperature. In the field, you do expect to have a gradient of temperature within a layer, of course. So the same is going to happen with humidity, relative humidity. And we have some models. We have conducted some computational mechanics models that show how is that change within the material. But it's exactly the same like temperature. We do expect that gradient, but for the characterization of the material, you want to know exactly when it has exactly this temperature, what is the expected value. So it's the same. So if you are going to include some of these models, these results into your models, you have to take into account that gradient and to put the proper material property in that layer. Okay? What is interesting is what I was saying before. You have both at the same time. You have temperature and relative humidity. So the material, the property has to take both into account, and we still don't know that. And the second one, very good question, the geometry of the specimen. The first thing is that we need to guarantee that it is a representative volume element. So that's why right now for that specimen, our nominal maximum aggregate size is 9.5 because the thickness of the wall is only 1 inch. But we follow several recommendations from people that have published a lot on hollow cylinder specimens, and they have conducted those sensitivity analyses. And we follow the recommendations of height, the final diameter, outlet diameter, and wall thickness to be sure it is behaving well. So we did that, and we try, during the implementation of the equipment, we considered that, in fact, we changed the mixture because we were concerned that probably it was not the best mixture to be tested. If you are going to increase the nominal maximum aggregate size, you need to increase also the wall thickness and probably the size of the specimen as well. So that's a good question. Yes?
Very nice work and really thought-provoking, I think, in the presentation. I was following with much interest. And I'd like to make a comment that especially when you bring different disciplines and findings and studies around results or known things in different disciplines, then you make some really good breakthroughs. I think your work is going in that direction. So being from geotech side, knowing well what the soils and partial saturation issues, how you brought basically that into the framework, that is, the suction concept. But I was surprised to find actually on the wet side, modules going up, like you mentioned too. However, I kind of, in my mind, thought about some similarities with Terzaki's effective stress principle. I think what you're probably showing with modulus going up in the wet condition is almost like the total stress concept with the pore water pressure.
Exactly,
now.
that's exactly it.
And can we define an effective modulus, like effective stress now, is separate from that kind of thinking? So that's what I was thinking in my mind. I don't know if you...
No, that's perfect. And what you said about bringing others' fields advancements to our field, that's exactly true. I mean, that's how we started, right? All the viscoelastic principles and everything coming from people from polymers, and we have been advancing using that. And the reason in our case is that, as I mentioned before, Professor Caicedo is half geotech, half pavements, and he is an expert in partial saturation. So when we started thinking about moisture, and I started showing my works in moisture damage, he told me, like, but do you have the retention curve of this material? I was like, the retention curve is only for abound granular materials and soils. It's like, no, it's for any porous material. It's like, yeah, of course. So that's partially the reason. And you are totally right. I mean, we should start thinking about if that high modulus that we see, what is the effective one? Because what we are seeing is the total effect of like two different media acting together or phases acting together.
Especially if you go back to the illustration on the west side, but you were showing like...
Probably.
You're showing the matrix full of moisture, exactly,
Yeah.
taking the compression. And the way that highest modulus properties on the wet side is really happening under compression. You're squeezing the whole thing, as opposed to the intention, it doesn't show.
Exactly.
So
It's exactly
there
that.
is the effect of more water pressure.
And that is exactly the reason why we believe that a higher frequency is even worse. Because at higher frequencies, there is no time to squeeze out. The water is there, and it's impacting strongly the response of the material. So, but it's totally true. I mean, if we see, I mean, this is not good for the material, in fact. This is not good. This is exactly what we see in unbound granular materials under saturated conditions. And that is why we use the concept of defective stress, of defective modulus and effective stresses. So this is part of what we need to start continuing doing, because it could give you the false impression that the material is more resistant. And it could be exactly the opposite. The material is more prone to degradation because of the presence of that pore pressure. Yeah, thank you very much. Yes, Dr. Alkali.
That's very, very interesting. I was just thinking a lot while you were presenting this, and it's really surprising to have like the modulus drop almost to half. Now, this is run as a complete modulus testing in a way,
Yes.
correct?
Yes.
Which means that the strain is low.
Yes.
So you have this in a humidity condition that you were testing for how long? I mean, you do condition it for some
Yes,
time, right?
I conditioned it until I guaranteed that they were in a steady state condition, that most of the times it took us around 2 to 3 weeks.
Okay,
That's
so that's a key thing here, is the amount of moisture that they got in, because it's not just a sudden thing.
It's not.
Something you're going to keep it for a while.
Mm-hmm.
The other thing which is interesting here, that later on you were doing maybe the analysis using the thin wall approach, correct?
Mm-hmm. Mm-hmm.
And your aggregate size is usually for these mixes,
Yes,
like
it's
what,
9.5.
2.5 time? 2.5? About,
Yeah, it
you
is.
mentioned something about the thin wall
Yes,
and the aggregate
we
size.
have like it's twice. We have 9.5 millimeters and almost 13 millimeters thickness. 1/3.
So
Yes.
you have like almost 3 times the walls,
Exactly.
3 times the maximum
Exactly.
aggregate size. So that's very, very appropriate. One of the things
That's the
that-
reason we were working with a previous mixture that had a nominal aggregate, maximum
Very
nominal aggregate size a little bigger, and then we started getting concerned.
Yeah, so what are you going to do with regular mixes? I mean, when we're
Ah,
going to go to the
we can do
field,
it.
how big the samples you want it, and what about the thick that.
We can do it. The only thing that we need to do in the machine is to change the size of the piston, and we can do that very easily. Not even the piston, the base. So we can adapt the machine to any size you want.
No, I'm thinking about now, will that make it like a thin wall for the analysis? If I'm gonna go with the 9.5 millimeter,
yeah, I understood.
So that will be a completely different analysis approach,
Yeah.
right?
That's true. Probably you cannot go up to
I mean,
probably 12.5 millimeters, but bigger than that,
Yeah.
that it could be a restriction for a hollow. I
the
mean, we
reason-
can still use the machine for
Yeah.
full samples, but then the shear response we
Here's
couldn't
something-
analyze.
Yeah, here's something really interesting that you may add to this. One of the things that we did in the field, that take a core and instrument the circumference from the core itself, because this is really important information. So have you thought about instrumenting this during the loading from inside the wall?
Yes.
Okay,
And
good.
it's yes,
All
because
right.
we need to be sure. In fact, we want to also have the Poisson's ratio, the complex Poisson's ratio and all that. We haven't done it, but we have the sensors. These are non-contact sensors, the ones that we are using that use the eddy current principle. So in total, we can have 8 non-contact sensors for radial, eggshell, and also to see what is happening in the wall from inside.
That would be really
Yeah.
nice. Yes, we did have some field measurements for that. So it's interesting.
Yeah, but that is a good point. And also one of our concerns were if we take the inner core and also the shell, is the gradation of the mixture changing for that hollow specimen? What about air voids? So we did all that studies. Gradation is almost perfect. It's less than 5% difference with the original gradation. And air voids are very nice because I don't know if you all know, but when you compact the specimen in the SuperPave giratory compactor, you have more air voids on top and bottom, and it's like a C shape. So you have less air voids in the center, but also radial. So you have more air voids outside and less air voids in the center. So when we remove the inner cylinder and the external shell, and also a little bit on top and bottom, we are having the most uniform distribution of air voids that you can get from a SuperPave giratory compactor specimen, which is also a very nice result for all these studies.
It's interesting to go back and at the time when they started Sharp, actually Carl Monosmith was pushing for the moisture test to be part of the testing, but it was very expensive equipment. I mean, you did your PhD moisture, so I'm sure you followed on that. It's unfortunate that it never become part of the testing protocol, so this is really good.
But answering your previous question about the size, just let me show you only this. The reason why this apparatus in Nottingham is so big is to take that into account. Because if you have a very larger aggregates, then the whole, for it to be like a thin wall specimen, then you have to have a huge specimen. But huge is huge. It's like to maintain. So they do that. So they actually like compact big slabs and take the specimens from it. But it also makes the whole equipment to be difficult to use. So it's perfect for those type of mixtures. But for mixtures that are a little finer, ours is much more versatile. So
Actually, the previous work on the hollow cylinder with the Nottingham group, Brown and Hyde reference, if you go back,
Yep.
that is designed for unbound aggregate testing in the hollow cylinder.
yeah, of course,
So then you need really thick walls
that's true.
for the aggregate.
In fact, our previous experience working with hollow cylinders is a PhD work of our geotech colleagues, the one that I was mentioning. And we have in our university a hollow cylinder tester for unbound granular materials. So it is really big because otherwise you cannot guarantee that the material is representative. I don't know if you remember probably from your visit there, but it's very big one, and the compaction and everything is a little challenging, but it's because of that, because of the size of the specimen. So you need to have a very big sample or a specimen.
Harold, he knows. I mean, this is the hollow cylinder for the granule material. It is a standard in France. I mean, that's how I read it. I mean,
This is the best equipment to study principal stress rotations,
Yeah.
actually, effectively. And because you get continuous rotation. This is the only equipment that gives you
It gives you that continuous rotation of principal stresses and complex stress paths. Yeah, in fact, one of the previous works, very famous one, is from Lyon, from Professor Di Benedetto in sands. So they started in clays, then in sands. Then the only machine that is the one that we have for big unbound granular materials, like coarse aggregate materials, and a couple of works in asphalt mixtures. But the machine itself provides a lot of possibilities. That's what we like. And in our case, the fact that we have a strong conditioning or environmental system as well, because that's one of our main research interests, to try to understand that interaction. Any more questions? Okay, thank you very much. So I promise that in our next models, we are start using proper data. And because that is very important. I mean, this is very important. That was one of the main motivations. We are very strong also in modeling, but without the proper input data, then what you model, is not very uncertain. Well, thank you very much.
We have meet and greet session. Dr. Caro, if you want to stay after the talk.